Hey everyone, welcome back. Today we have a truly fascinating explainer lined up for you. We are going to explain completely how the entire landscape of artificial intelligence is fundamentally shifting. Because, let's face it, if AI keeps growing at its current explosive rate, we literally won't have enough power on the grid to run it. We're actually moving away from traditional software-heavy deep learning, and we're diving headfirst into biologically inspired physical hardware. It's a massive shift. So let's dive into this and figure out how mimicking the squishy human brain is solving AI's absolute biggest bottleneck.
To really grasp why this shift isn't just cool, but mandatory, you just need to think about this staggering number, 10,000 times. That is the difference in energy efficiency between your biological human retina and traditional computer hardware when they're completing the exact same visual tasks. 4 orders of magnitude. Our brains, our sensory organs, they do incredibly complex math with practically zero power drain. How? Well, by using a completely different architectural blueprint than the computers sitting on our desks.
And that brings us to the core of our current computing crisis. Modern deep neural networks are brilliant, don't get me wrong, but they are essentially brute force engines. They relentlessly crunch massive amounts of data with constant mathematical calculations, which naturally generates a massive power drain. Biological brains, on the other hand, rely on sparse data. They are spike-driven. That means they only activate when absolutely necessary, running on ultra-low power. So, to scale AI into the future, we've basically reached a point where we need it to act a lot less like a calculator and a whole lot more like a biological brain.
All right, so here is our roadmap for today's explainer. We'll start with AI's growing power problem, then look at the 3 generations of AI architecture, explore how biological brains actually learn, translate that into the math of spiking, and finally, look at the physical construction of artificial synapses.
Okay, part 1. AI's growing power problem.
We have to start by acknowledging the absolute wall that current deep learning is hitting. While these networks give us total miracles in image recognition and object detection, they have some severe foundational flaws. First, they require massive data sets just to learn super basic concepts. Second, they act as these unexplainable black boxes, where their internal parameters don't even have specific physical meaning. But the most critical flaw? That's the relentless multiply-accumulate, or MAC operations. In a standard DNN, the units are constantly doing math, like all the time, even when no useful information is actually flowing. Multiply that by billions of parameters, and you end up with an entirely unsustainable power consumption model that simply cannot be the future of computing.
Which leads us to part 2, the 3 generations of AI.
So, to escape this computing bottleneck, we have to rethink the very units of computation themselves. The first generation was the Boolean perceptron. Think simple 0 or 1 digital inputs compared to a threshold to output a 0 or 1. Pretty basic. The second generation introduced continuous values and nonlinear activation functions. This gave us the deep neural networks we use everywhere today. But the real breakthrough is the third generation, spiking neural networks, or SNNs. Instead of processing continuous numbers in every single cycle, SNNs use temporal pulse trains. They encode information based on the exact timing of a spike. And the magic here is that if there's no spike, there's no math. This drastically cuts down on power consumption while handling temporal information beautifully.
All right, part 3, how biological brains learn.
Now, to actually build these spiking neural networks in hardware, we have to explain completely the biological blueprint that inspired them. See, in our biological brains, learning and memory aren't stored in lines of code on a hard drive. They're a literal physical change. This is driven by a mechanism called long-term potentiation, or LTP. Basically, it's the persistent strengthening of a synapse based on recent, high-frequency patterns of activity. Put simply, when 2 neurons fire together frequently, their physical connection literally gets stronger. That's exactly how we learn so efficiently without needing a massive server farm full of training data.
It's truly amazing when you break down the actual physiology of this, say between a presynaptic CA3 neuron and a postsynaptic CA1 neuron. During normal transmission, neurotransmitters are released, but ion flow is actually partially blocked. However, when rapid spikes arrive during high-frequency stimulation, a huge depolarization occurs. This physically relieves the magnesium block, which allows calcium, sodium, and potassium ions to just flood into the cell. And this sudden influx triggers a cascade that literally inserts brand new receptors into the postsynaptic cell. I mean, the brain's physical hardware is literally rewiring itself in real time to store a memory. How cool is that?
Moving right along to part 4, the math of spiking. Obviously, we can't build computer chips out of squishy biological brain matter. So the crucial next step is translating that physiological reality into hard mathematics. And the brilliant realization here was that the biological cell membrane acts exactly like a capacitor. It stores electrical charge. The ion channels, the ones letting elements in and out, they act just like variable resistors in batteries. And the membrane potential is, well, simply voltage. By equating wet biology to standard electronic components, engineers realized they could write super-precise differential equations to model perfectly how a neuron fires.
And this mapping gives us the incredibly elegant leaky integrate and fire model, or LIF. Think about the narrative happening inside the cell here. When a neuron receives a pulse of input current, the charge accumulates over time because the cell membrane isn't a perfect insulator. But it also naturally leaks away. The neuron only outputs a signal, a spike, if that integrated voltage hits a very specific, critical threshold before it leaks away. Once it fires, boom, it drops immediately back to a resting state. It's a mathematically precise, gorgeous way to simulate biological learning.
And that brings us to the grand finale, Part 5, Building Artificial Synapses. This is definitely the most exciting part of the explainer. We're talking about turning those mathematical models into literal, physical hardware. We're moving completely away from a software training ecosystem and jumping into physical circuit diagrams. We're using novel devices like ReRAM, phase change RAM, and magnetic RAM. These devices are physically wired to act exactly as artificial synapses and postsynaptic neurons. They replicate that exact leaky integrate and fire dynamic natively right in the hardware itself. We are literally building artificial brains in silicon.
And the absolute hero of this new hardware revolution is the memristor, specifically resistive RAM, or ReRAM. A memristor is a non-volatile memory device whose electrical resistance changes depending on the voltage applied to it. The sheer magic here, and the reason why this matters so much, is that it remembers that state even when you pull the plug and the power is turned completely off. By simply tuning the resistance of this tiny electronic component with voltage pulses, engineers can perfectly mimic the physical strengthening and weakening of a biological synapse.
The physical mechanics making this happen are absolutely fascinating. It all happens in 3 steps. First up is forming. An initial high voltage literally knocks oxygen atoms out of the device's oxide lattice, and that creates oxygen vacancies that form a physical conductive filament. Step 2 is the set phase. Applying voltage causes ions to migrate, reinforcing this filament and switching the device into a low-resistance state. That's just like a strong biological connection. Step 3 is the reset phase. Applying a reverse voltage actually ruptures the filament, returning it to a high-resistance state. By carefully controlling these migrating oxygen ions, we are perfectly tuning the physical memory of a circuit.
So, to bring this all together, this biomimicry offers what we call the neuromorphic advantage. By using memristors and SNNs, we eliminate those power-hungry MAC operations entirely. The system operates purely on sparse spike data, only drawing power when absolutely necessary. Even better, we unify memory and processing in the exact same physical location. That means no more constant, costly shuttling of data back and forth. Ultimately, this enables ultra-low power in-sensor computing. Just imagine an artificial retina in your smartphone doing complex AI processing right on the camera sensor itself, instantly, without draining your battery or needing to connect to the cloud at all.
We are moving from the massive power drain of deep learning servers to the incredibly efficient, spike-driven logic of memristors. It's a fundamental rewrite of how we process information as a species, and it forces us to ask a pretty heavy question. What happens to the future of technology when artificial intelligence no longer just simulates human learning in software, but actually physically embodies it in hardware? It's a profound shift. It's happening right now, and it's going to change everything. Thank you so much for joining me on this explainer, and keep questioning the future.